Let's talk about quantum computing from the ground up, in a way that actually makes sense when heard out loud. We already know how ordinary computers work. At the deepest level, everything runs on bits, and a bit can only ever be 0 or 1. Billions of tiny switches flip between those two states, and by combining them cleverly, we get everything from spreadsheets to video games to the internet. Now here's the key limitation. As problems get more complex, the number of possibilities a classical computer has to keep track of can grow extremely fast, often exponentially. For some problems, even the best classical computers would need more time than the age of the universe to finish. That's a fundamental limit of how classical information works. At the same time, the physical world itself does not behave classically. Atoms, electrons, photons, and molecules follow the rules of quantum mechanics. Nature, in some sense, is already computing using quantum rules. Quantum computing is the idea of building computers that follow those same rules, so that certain problems become tractable instead of impossible. The basic unit of quantum information is called a qubit, short for quantum bit. A classical bit is either 0 or 1. A qubit is different. A qubit can be in a state we describe as a combination of 0 and 1 at the same time. Mathematically, we write a qubit as alpha times 0 plus beta times 1, where alpha and beta are complex numbers, and the squares of their magnitudes add up to 1. What does that actually mean in plain terms? It does not mean the qubit is secretly 0 and 1, and we just don't know which. It means the qubit genuinely does not have a definite value until we measure it. Before measurement, the qubit carries a kind of weighted possibility for being 0 and a weighted possibility for being 1. When we measure a qubit, something important happens. The quantum state collapses. We only ever see a classical result, 0 or 1.
The probability of getting 0 is the magnitude squared of alpha.
The probability of getting 1 is the magnitude squared of beta. So quantum information is probabilistic by nature, but not in the same way as rolling dice. The probabilities come from amplitudes that can interfere with each other. This idea of interference is absolutely central. To see why, we need to talk about what happens when we have more than one qubit. There are 4 possible states: 0, 0, 0, 1, 1, 0, and 1, 1. A classical computer is always in exactly one of those states at any moment. With 2 qubits, the quantum system can be in a superposition of all 4 states at once. With 3 qubits, 8 states. With n qubits, 2 to the n states. The size of the state space grows exponentially. Now comes one of the most non-intuitive ideas in quantum physics: entanglement. Their states are linked in such a way that we cannot describe each qubit independently anymore. The system has to be described as a whole. For example, 2 entangled qubits might be in a state where measuring the first qubit immediately determines the result of the second, even though neither qubit had a definite value beforehand. This is not just correlation in the everyday sense. There is no classical explanation that reproduces these correlations without quantum mechanics. Entanglement is not just a curiosity. It is one of the main resources that give quantum computers their power. Without entanglement, quantum computers could be efficiently simulated on classical machines. So how do we actually compute with qubits? The answer is quantum gates. Just like classical computers use logic gates such as AND, OR, and NOT.
Quantum computers use quantum gates. These gates are operations that smoothly rotate and transform the quantum state of qubits. Mathematically, they are unitary transformations, which means they preserve total probability. Some gates act on a single qubit, like the Hadamard gate, which creates superposition, or rotation gates, which change the relative weights and phases of 0 and 1. Other gates act on 2 qubits, like the controlled NOT gate, which is crucial for creating entanglement. A quantum computation is built as a quantum circuit.
We start with qubits in a known state, often all zeros. We apply a sequence of quantum gates. Then, at the end, we measure the qubits and read out classical bits. At this point, a very common misunderstanding needs to be addressed. People often say that quantum computers try all answers at once. That sounds appealing, but it is misleading. If we simply put all possibilities into superposition and then measure, we just get a random answer. That's useless. The real power of quantum computing comes from interference. Quantum algorithms are designed so that the amplitudes of wrong answers cancel out, while the amplitudes of correct answers reinforce each other. After the interference pattern is set up correctly, measuring the system gives the right answer with high probability. This is why designing quantum algorithms is hard. The challenge is not creating superposition.
The challenge is choreographing interference so that the final measurement is meaningful. Now let's connect this to actual algorithms. One famous example is Grover's algorithm. Suppose we want to search an unsorted database of n items. A classical computer needs on average n over 2 checks. Grover's algorithm can do it in about the square root of n steps. That's a quadratic speedup. It doesn't sound dramatic for small n, but for very large n, it is significant. Another famous example is Shor's algorithm. This algorithm can factor large integers efficiently. Factoring is believed to be hard for classical computers, and modern cryptographic systems like RSA rely on that hardness. A large, fault-tolerant quantum computer running Shor's algorithm would be able to break those systems. That is why there is so much interest in post-quantum cryptography. Perhaps the most natural application of quantum computing is quantum simulation. Quantum systems are extremely hard to simulate on classical computers because the state space grows exponentially. A quantum computer can naturally represent and simulate other quantum systems. This has huge potential for chemistry, materials science, and drug discovery. It is equally important to understand what quantum computers are not good at. They are not faster at everyday tasks like browsing the web, editing documents, or running operating systems. For most problems, classical computers remain the best tool. Now let's talk about reality. Quantum states are fragile. Any interaction with the environment can cause decoherence, which destroys superposition and entanglement. Quantum gates are noisy. Measurements are imperfect. This is why building quantum hardware is so difficult. To overcome this, quantum computers rely on quantum error correction. Error correction encodes a single logical qubit into many physical qubits, so that errors can be detected and fixed without measuring the quantum information directly. This works in theory, but it requires a large overhead. Depending on the technology, thousands of physical qubits may be needed to make one reliable logical qubit. Today's quantum computers are often described as being in the NISQ era, which stands for Noisy Intermediate Scale Quantum. These machines have tens or hundreds of qubits, but they are not yet powerful enough for large error-corrected algorithms like Shor's factoring at cryptographically relevant sizes. They are mainly used for experiments, research, and learning how to control quantum systems better. There are several different approaches to building quantum hardware. Some systems use superconducting circuits cooled to near absolute zero. Others trap individual ions with electromagnetic fields. Some use photons, and others use neutral atoms arranged in precise arrays. Each approach has advantages and trade-offs in speed, error rates, and scalability. Stepping back, here is the big picture. Classical computing is about manipulating definite bits using deterministic logic. Quantum computing is about manipulating probability amplitudes using the rules of quantum mechanics. The goal is not to replace classical computers, but to extend our computational toolbox. When quantum computing works, it works because we carefully prepare superposition, create entanglement, apply gates that cause interference, and then extract just enough information through measurement to get a useful answer. It is subtle, fragile, and mathematically deep, but for certain problems, it changes what is computationally possible. That is quantum computing in essence, controlling the quantum behavior of matter to compute in ways no classical machine can.